So I must say that I could not live up to that standard they had set for us, but whatever little droplets of their teaching trickled down to my interior have remained extremely enriching to this remember. So, however, I must say that, this is not the story for everybody. In rather pleasing contrast to what I said now, we have as our speaker today a person who really matched up to the standards set by AKR. That is Professor Ashoke Sen. And that Professor Ashoke Sen is probably the best pleasing contrast to the kind of failures of people like me. Was obvious not from any other things. I have heard, me and some others heard Professor Rai Chaudhary himself making similar observations about Ashoke Sen. That said, we don't need any further description of the many achievements, accolades, and recognitions that he has received all over, where there are very few are left to be received. But rather, let me say that he is treated as a great contributor in string theory, which is undoubtedly true. But just calling Ashoke a great string theorist is a mistake. He should be called a great figure with his overall perception of physics. And he is one of the widest and deepest physicists I have seen in my lifetime. Broadest and deepest. In fact, having worked with him in the same institution for nearly 25 years or maybe a little more, I can say that is impossible. It is impossible to be within a few hundred meters of Ashoke and not benefit from his presence at the primary, secondary, or tertiary levels. So now the fact is that all of us are within 50 meters of Ashoke's presence. So without any other further introduction, maybe I can mention that he was a student from 1972 to 75. Without anything else, let us use this opportunity of benefiting from his presence by listening to what he has to say about classical gravitational radiation and quantum gravity. Professor Ashoke Sen.
So before Professor Sen's talk starts, so if I may interrupt, so the students of Presidency University would like to present some tokens of appreciation to Professor.
After the talk.
Oh, okay, maybe that will be better.
After the talk.
Yeah, they would like to present some mementos to.
It is after the talk.
Sure.
So this is the result. Then changer is now equally working. We can just.
এখান থেকে করতে হবে যেহেতু এই কলার মাইক তো নেই, এটা সাইড চেঞ্জার আছে।
এখান থেকে দাঁড়িয়ে করতে পারো তাহলে টাইটেল পেজটা টাইটেল পেজটা কি আমি বলতে কি অর্ডার দেখলাম নেই।
আচ্ছা, ডেস্কটপ তো করলে হবে না, পুরোটা করতে হবে।
পুরোটাই করেছি।
পুরোটাই করেছি।
এটা কেন আসছে এটা আসার কথা না, বাট ঠিক আছে দেখতে পারি। এখানটাতে আপনি এইটা দিয়ে দিন। এই
ঠিক আছে, ঠিক আছে।
কি হলো, এটা কেন হচ্ছে এরকম?
স্লাইড শো করতে নট স্ক্রিন, স্লাইড শো করতে হবে।
Slide show, not full screen. Now the changer should be on. Audio is full. Changer should.
হ্যালো, ইয়া
চেঞ্জেস আর কিন্তু আমি এটা করে দিচ্ছি।
ঠিক আছে, এটা দিয়ে যদি না হয় তাহলে এটা দিয়ে ডিরেক্ট।
এটাই করে বলতে হবে,
এটাই ঠিক আছে।
এটা আটকে গেলে আবার
ঠিক আছে, আমি এটা দিই। ওকে,
কলার মাইক
লাগবে, কলার মাইক তাহলে এটাকে আমি তুলে দিচ্ছি। হ্যাঁ, ঠিক আছে।
Hello.
Am I audible? Am I audible? Yes, yes. 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 Yes, yes.
Okay, first of all, thank you, Biswarup, for your introduction. And I'd like to really thank Chetana and all the other organizers for giving me this opportunity to come here and speak, because it's really a great honor for me to be giving this AKR Memorial Lecture. There is a laser pointer here somewhere, this one. Okay, so I was really fortunate to be taught by AKR from 1972 to 75, and he taught us thermodynamics, as I think you have heard also from others, right? That was one of the subjects that he taught during our BSc class. Unfortunately, I was not here for MSc, so I didn't attend his classical mechanics course. But I, of course, have read the notes that my friends took during his MSc teaching. Now, you have already heard that he was a great teacher, but he also cared deeply for his students. And here I can just mention one example which perhaps is unique to my generation. That the time when I was studying in President's College was the days of political turmoil. And often there is violence in the campus, often from people from outside. And you will see students getting beaten up once in a while. And several times I remember the scene where some outsiders have come to beat up somebody in the principal. And I can also visualize the whole row of teachers standing and blocking their path. And AKR was in the forefront, arguing with the outsiders as to why they shouldn't beat up students. And AKR always won. Right? I have never seen any time where the students actually could come inside and cause violence inside the department. So that was AKR. And we did have first-hand experience of this during our college days. There is, however, one aspect of AKR that we didn't know about, even though we had some inkling. And that is the following. Today, if we go to a conference on general theory of relativity, the equation that we hear of most often is Einstein's equation. Einstein is the one who started this subject. But Raychaudhuri equation comes a close second. And during our college days, we had no inkling how important this one was. We had some vague idea that it was good in research, but not how much important it was. And today I should say that we hear about the what Hawking and Penrose influenced by Raychaudhuri's equation, but Raychaudhuri's equation certainly has a very, very wide application. Not only in classical theory of gravity, but also in some aspects of quantum theory of gravity. Okay, so it's really something that is used very widely now. So today we can really look back at AKR as an example of a great teacher, a great scientist, and also a great human. So with this, let me begin my talk. So my talk is classical gravitational radiation using quantum gravity. Okay, and since I work in the subject of quantum gravity mostly. Since AKR's work was mostly classical gravity, I thought maybe this is a good topic to discuss, which, even though none of this is directly related to AKR's work, but at least it has overlap with classical gravity and quantum. So let me begin with the kind of problem that we'll try to address this talk. So let's suppose that you have a violent explosion in space, which may consist of a bound system that breaks apart into fragments. So during this process, it will emit gravitational radiation, or what we call gravitational waves. And if you have a detector T placed far away somewhere in the universe, it detects the radiation as ripples in space-time. And the examples of such violent explosion are supernova, where a star basically blows up, or a merger of two black holes. So you can think of this as a bound system of two black holes, but suddenly it just explodes into gravitational waves. One can also consider a somewhat more general situation, that a collision, where several objects come together They collide and then they move apart. And this will also produce gravitational radiation. And one example of this is what I can give as an example as a bullet cluster. Okay. Bullet cluster is a supercluster of galaxies, one supercluster of galaxies passing through another supercluster of galaxies at a speed of about 1% of the speed of light. Yeah, and 1% of speed of light is a really large speed as far as the standard what is in the universe is concerned. And this cluster of galaxies are also extremely massive, each weighing about 10 to the 14 times the mass of the sun. So these are the kind of processes which can produce gravitational waves in the universe. Now, in general, if you want to calculate what kind of gravitational wave will be produced during such processes, it's complicated. It's complicated for two reasons, or at least two main reasons. One is that when the objects are close, they may undergo complicated nuclear and other interactions that are not fully understood. Right? For example, when a star blows up, inside the star, a lot of nuclear physics is happening. Yeah, we may not quite understand what kind of interactions are happening inside the star. But the other reason why it's complicated is that gravity, as formulated by Einstein, is described by what is called nonlinear partial differential equations, unlike the linear differential equations of electromagnetism. So typically, computing electromagnetic waves emitted by a process involving charged particles is much simpler than gravitational waves that is emitted in the collision of objects. So because of this, even if the interactions are purely gravitational, for example, when two black holes merge, there's nothing else you have to deal with, right? No nuclear force, no electromagnetism, it's only time. But even then, to calculate what kind of gravitational wave will come out of the merger of two black holes is a complicated process, and people do it mainly numerically. You have to run computers to figure out what happens. Now, it turns out, surprisingly, that some results in quantum theory of gravity, which are known as Hawks-Graviton theorem, and I'll say a little bit more about them later, can be used to get analytical results on some aspects of classical gravitational waves. And this is what I'll try to explain, what kind of results we get and how we get. So let me begin with an introduction to gravitational waves, what they are. But I'll begin with electromagnetic radiation, which probably many of you are familiar with. So electromagnetic fields, as we learned in our BSc or MSc days, can be described by what is called a four fields, four independent fields which you can combine into a vector, of which the first one, A0, is the electrostatic potential, whose gradient gives the electric field. And then there is other three components which give the magnetic vector potential. So when charged particles interact and as a result accelerate, they will produce electromagnetic radiation. Okay, so what is electromagnetic radiation? That's time and space varying electric and magnetic field. Okay, that's a simple description. But the way you should distinguish an electromagnetic radiation from, say, electrostatic field, like a stationary charged particle also produces electric field. The main distinction between a static electrostatic field and electromagnetic radiation is that if we go far away from the source, okay, where the charged particles are, the electric and magnetic fields associated with electromagnetic radiation fall off as 1 over r, where r is the distance to the source, and not as 1 over r squared, like what happens for electrostatic. So this is one of the distinct features of radiation from static electricity. Now, gravitational radiation is somewhat similar. So, in the general theory of relativity as formulated by Einstein, a gravitational field is a symmetric two-index field. Okay? Unlike electromagnetic field, which had only one index, a mu, right, where mu runs over 4 values. Gravitational field is a 2-index field. And what this measures is distortion of space-time. How are they produced? They are produced just like electromagnetic radiation. Accelerated motion of objects carrying mass or energy produce gravitational radiation. Because mass, as you know, is the source of gravity. And once you take it back on special relativity, that becomes energy as the source of gravity. So let me give a little more detail of how gravity affects space-time. So let's suppose that when there is no gravitational field, we have two objects in space which are separated by some distance L. They are on some direction in space. Then, in the presence of gravitational radiation, when gravity is present, the distance will change to something else, where this n hat, this is a vector, okay, which gives the direction along which the two objects are separated. Okay, so n hat is a vector, unit vector, and hij is the component of this field. H that this is the gravitational field. So, in short, presence of gravity changes the distance between two objects in space. Okay, if the original distance was something, then the same two objects, when gravity moves, when a gravitational wave passes, the distance will change. And that change will depend on which direction the objects are separated. Right? That's where this n comes in. So here is the same formula again. Okay, how the distance changes when gravitational wave passes through. But we see that because this is distance direction dependent, if we have an interferometer, okay, so here I have to draw an interferometer where a beam of light comes in, right? Then there is a semi-transparent mirror. Okay, it's partially reflected, partially transmitted. Then there are two mirrors here. Okay, they get reflected back from the mirrors. They are combined here and detected in some detector. Right? This is an interference pattern that you see. So effectively, what this interferometer is sensitive to is a difference in length between this side and this side. Okay, because that measures the phase difference between the light coming from here and the light coming from here. So now you see that when a gravitational wave passes through, these distances will change. And in general, they'll change by different amount because they are oriented in different directions. Right? This is the one vector n, and this is another vector n. They are different. So the change in the distance here will be different from the change in distance here. And we'll see some oscillation in this interference pattern. Okay, and that's what we have. That's how the gravitational wave detectors work. So then you have ordinary interferometer, but you try to superpose ordinary light and measure certain changes, certain oscillations in the interference pattern. So this is how you detect. But the problem that you will be interested in is how you calculate what kind of gravitational wave is produced. Right? Suppose you have detected some gravitational wave. You have to know what kind of source could possibly produce such gravity. For that, you need to know that given a source, what kind of radiation will it produce. So now let me fix the conventions before I give you some more details, the results. So C in my convention will denote the speed of light. Capital G will denote the Newton's gravitational constant. We will denote the space-time coordinate. This is the relativistic notation, okay, by this x mu, okay, where mu runs over 0 to 3. So x0 typically is measures the time coordinate. Where precise definition of x0 is the speed of light times time, and x is the usual space coordinate. We will also introduce the 4 momentum, whose zeroth component is the energy divided by the speed of light. And then the other 3 components are the usual momentum that you are familiar with. These will be 2 matrices, okay, same matrix. Okay, one written with indices down, one written with indices up. These are 4 by 4 diagonal matrices, and the diagonal elements are -1, 1, 1. Everything else is 0. With this, I'll denote the scalar product A dot B, okay, by this notation. Okay. And when you write it out explicitly, it's this, right? Because eta is a diagonal matrix, so the 0, 0 component is -1, and the other diagonals are 1. So in this notation, you can see that if we calculate P dot P, right, you have this 4 momentum P. So it's minus P0 square plus P vector square. But P0, I have already said, what is it? It's energy over C, right? So minus E square over C square plus P square. And now if you use the relativistic relation between energy, momentum, and mass, you can easily convince yourself that this object that you see here is minus m squared times c squared. So these are the various notations I'm going to use in the various formulas that I'm going to show. The last notation that I'm going to mention is what is called the summation convention. This is just a convention, but this is useful. That whenever an index appears twice in a formula, we'll assume that it sums from 1, 0 to 3. So here, for example, right, we have eta mu nu p mu. This mu indexes appear twice here, right? So this means that mu is summed from 0 to 0. Right? That this is what we need. It just helps us in removing a lot of the summations. Right? Otherwise, the formula will have the summation symbols every time. And the final notation is that when you have, if you have a vector with indices written down, then we also define a vector with indices written up simply by multiplying by the eta. Okay, so B with lower index mu is eta mu rho times B mu rho. Yeah, you see here the rho is repeated twice, so it's already sum. Similarly, A with upper index is eta with upper index mu rho, A with lower index. So in this notation, you can easily convince yourself that B0, for example, right, is eta 0 rho B rho, but only the rho equal to 0 contributes because eta is a diagonal matrix. So B with lower 0 is minus B with upper 0, and then these are all. So perhaps many of you are familiar with this, but for those who are not, yeah, I thought I'll just make everything explicit so that when the formula reads, you will know what it is. Okay, so now I'll describe the kind of results that one can get, and then I'll describe what kind of logic one uses to get to those results. So let's go back to your problem. Right? You have a scattering in space. Okay, what is scattering in space? A set of objects come in, collide, and then go out. Okay, the explosion is a spatial case of this. Explosion means that what comes in is only one object, and then it splits into many objects. Right? So scattering includes explosion as a spatial case. So you have a scattering. Okay, the incoming momentum. Okay, and we're talking about the incoming 4 momentum. Incoming 4 momentum, which are denoted by primes, like P1 prime to Pm prime. And outgoing 4 momentum are denoted by P1 to Pn. Right? So M objects coming in, N objects going out. So this is some region in space time, okay, where the scattering is taking place. And just to make our notation simple, we will choose the origin of space time to be inside this scattering region S. Right? Which means what? Which means that we will choose the origin of space to where the actual scattering is taking place. And we will choose the origin of time E equal to 0 to be around where the time when the scattering is taking place. Right? Something comes in, goes out. Now suppose that during this process, okay, first of all, during this process, of course, there will be gravitational waves produced. And imagine that you have a detector T, right, sitting somewhere far away, which receives the signal, the gravitational wave signal, by using those interference. So the peak of H mu nu, okay, the signal of course has some amplitude, right? It comes in, oscillates, and then it dies out. Gravitational wave has passed through. So the peak of the signal, okay, or around the peak of the signal will reach the detector at some point T, at some time T0. Okay, and you can actually calculate what T0 is. If everything propagated at the speed of light, then this would be just the distance to the detector R over the speed of light. But it turns out that there are corrections to this formula. And these corrections come because of the fact that there is gravitational drag on the gravitational radiation. And in fact, this is not just gravitational radiation, everything is dragged. Because even light is dragged by the same amount. So it's not that gravitational radiation will slow down, light will also slow down. Light and gravitational wave will reach at the same time. But the time is not just R over C, there is a correction. Yeah, but whatever it is, that's what I'm going to call it at some later time where the gravitational radiation is reached. Now, we define inter-rate time. Okay, as a difference between the actual time when the detector is where at the time at actual time at the detector and the T naught, which is the peak of the signal. Right? The detail of you don't have to really look T naught sharply, right? Because there may be multiple peaks, for example. But T naught is roughly when the bulk of the signal is passing. So what we'll focus on, okay, and that's because this is where quantum gravity helps us understand the results of classical gravity, is what kind of signal we'll observe at large positive U and large negative, which means that the gravitational wave passes through the detector, there is a signal, but we'll be interested in looking at the tail of the signal at very late time or early time. Not that that's the only thing we measure, but that's the only thing we can calculate reliably without using computers. That's the reason why you are interested in such signals. And so what I'll do is I'll try to give you a formula for this. What happens at large positive U and large negative. So giving a formula for gravitational wave means you have to specify what h mu is. Right? H mu is a function of. Because h mu is a gravitational field. Once you know h mu, you can calculate how much the interference will be, how much signal we'll see in the interference. It turns out that the formulae are a little simpler, not in terms of h mu, but if you use this new tensor, new object E mu, which is given here. Some combination of h mu and eta mu. But this actually contains exactly the same information. If I give you E mu, you can reconstruct h mu because this formula determines E mu for a given h mu, but this can be reversed, and you can show that if somebody gives you E mu, then you can calculate h mu by this formula. Same formula in fact. Reverse. So you are not losing anything by giving E mu. It's just that use of E mu makes life a little simpler in how you write the form. Now, what one finds is that if you look at the time proportional to R inverse, which is the radiation, right? We are not interested in the first outcome, right? 1 over R squared terms. They are there, but they are so small that if you are far away objects, you cannot even see them. So, time proportional to R inverse, the radiation, is the form of E mu at large positive U, which means late time. After the signal has passed, you wait for a while, and you see how the signal looks at late time. Has a structure like this, okay, with some coefficient A mu, then there is a 1 over U term with coefficient B mu, 1 over U squared log U, coefficient F mu, and then there are terms which are subdominant, right? This certainly falls so faster than any of these. And for large negative U, it has a similar form, except that there is a constant piece over here. Right? E mu is 0 at early time, because there is no gravitational wave. Now, the result of this quantum gravity analysis is that these coefficients that appear here, they can be calculated solely by the phone momenta of the ingoing and outgoing objects without requiring any detailed knowledge of the details of the scattering. So let me repeat again. So some objects coming in, some objects going out. In general, these objects have very complicated interaction, right? Because they could interact by nuclear interaction, for example. Gravity is non-linear, so the calculation is hard. But if we are interested in the late and early time behavior, then these coefficients can be calculated purely in terms of what came in and what went. And of course, the angle at which the detector is. Right? Because you have to know where the detector is to see what the signal is. So in the next two slides, I'm going to give you the formula for these coefficients. But the only purpose of giving the formula is to convince you that they exist, not that the formula themselves are very illuminating. But the only thing that I'll try to point out is that the formula, the only terms that the only variables that we need for that formula are just the momenta of the incoming particles and outgoing particles and the direction in the detectors. Okay, so don't try to follow the formula at any deeper level than that. You guys are not going to be very liberating. Here are the form for these three coefficients: A mu, B mu, and C mu. And you can see that as promised, right? It involves, of course, the fundamental constants. Right? G, C, the Newton's constant, the speed of light is the distance. And all that it involves are the momenta of the incoming and outgoing particles and this vector n, right, which are defined here. So the first component, the zeroth component of the vector n is by definition 1. And then this is the vector x over r, which means it's giving the direction into the detector. And that's all you need to calculate these coefficients, A, B, and C. And F and G, which I'm going to give in the next slide. So let me put the formula again. So A, B, and C are these formulae, right? These three coefficients, and then this F and G, which I'm going to give in the next slide. So here are F and G. It's the more complicated portion, but it uses exactly the same name. Right? There's no further input that is needed. Right? The P prime, and the vector n. The vector n. Right? And the masses of the particles, the masses are related to the momentum, right? As you saw. If you have the four momentum, that's the four components of the momentum determine what the mass is. So let me say a few more words about the formula. So here is the formula again, right? E mu at late time and at early time. This term A mu, this has been known from the 70s. This is what is called the memory term. So what this is saying actually is somewhat strange. If you think of it, normally you would think that when the wave passes through, there is some oscillation, and at the end of the oscillation, you go back to zero. Right? So I would expect that, okay, let's imagine that there is this interferometer. We have set it up in a way where there is pure destructive interference, there is no signal. Then the gravitational wave signal comes, it starts oscillating. And at the end of the oscillation, it should again go back to where it started, then the destructive interference. But this memory term says that that doesn't happen. It actually causes a permanent change in the state of the detector after the passage of the gravitational radiation, where as U goes to infinity, E mu doesn't go back to zero. This is a somewhat strange effect of gravitational waves, but this is there. Yeah, this was understood classically, as I said, in the 70s. These are new. Okay, B, C, F, and G. Right? These are what we call tail terms. These terms, okay, are not known earlier. They are derived using this quantum theory. But of course, once you have idea, you know the formula. It's a purely classical result after all, right? So you can derive it using classical methods. It's just that it was not there, but it was not noticed earlier. Right? And this formula exists. And by the way, I should say that there is a similar formula for electromagnetism. And I mean, if you look at the Jackson, and Jackson has a complicated formula, but if you again look at the late and early time, right, you will find that there is 1 hour in behavior that comes out. Again, you can relate it to this quantum partial electromagnetism. So this one I have already said, right? Let me emphasize again that these can be expressed in terms of momentum of incoming and outgoing objects without knowing what force is operated and how the objects move during the scattering. Okay, and this is a consequence of soft gravitons theorem that I'll explain later in this talk. And I should contrast this, and if you have to compute this gravitational wave at finite time, it will depend on the details of the scattering process and it will involve very complicated calculation. right? Because of the non-linearity of gravity, as well as because of other forces that act between these objects. Other point, this is about the formula. If you look at the expression for these coefficients, A mu nu, B mu nu, and F mu nu, let me go back to the formula for it. Let me go back to A mu nu. So this is simpler, A and B. You see that C, which is the early time, C was the early time. This depends only on the incoming momentum, right, and not on the outgoing momentum, because it's only our P prime are the incoming. So C depends on the incoming momentum. A and B, on the other hand, depend both on the incoming momentum and outgoing momentum. Now, this is the outgoing momentum of everything that goes on. Which means that if you have, say, a gravitational waves produced, in this formula, you should also include the energy or momentum that is carried out by gravitational waves. That makes this formula a little clumsy, because in order to calculate the date time gravitational wave, you have to know exactly what kind of gravitational wave was emitted. It's not very illuminating. Well, it's still useful, but it's hard to apply, because you have to first numerically determine what kind of gravitational wave is emitted, then put it in this formula to figure out what the date time is. And the same thing we can say for F and G. So for A mu nu, okay, the memory term, this is what is sometimes referred to as nonlinear memory. Okay, the memory that is produced by the gravitational wave itself. But it turns out that because of some miraculous cancellation in D and F, right, even though the formula that I showed you had sum over all final state particles, including gravitational waves, which you can also think of as massless particles. Massless particles going out, because these gravitational waves are like massless particles. These can be expressed in terms of massive state. Right? So there is a way to rewrite this formula, which depends only on the massive particles that are produced, not waves. And the formula will still be valid. So let me explain what one has to do. So in V mu nu, okay, this is the coefficient of the 1 over u at length time. The rule is that you just drop the massless particles or radiation contribution in the sum of our final states and add this contribution, where Pi is the total incoming momentum and Pf is the total outgoing momentum, but carried only by the massive particles. So the difference between Pi and Pf is accounted for the massless particles that are emitted. But the formula depends only on the momentum of the initial state particles and the final state massive particles. Right? You don't have to calculate the final state gravitational wave produced to calculate to use this formula. And similarly, in F mu nu, there is a similar simplification that we drop the massless particles and radiation in the final state and then replace it by this compensating term. Now, I should emphasize that these are not new formula, right? This is the same formula that I showed you earlier. So, this formula is still valid. Is that this formula for F mu nu can be rewritten by dropping the sum over all the final state massless particles and replacing it and adding that extra contribution which involves the massive part. This is still a mystery why it happens. Right? It's just an observation that you can do this. But clearly such an observation must have some deeper meaning. Why is it that you can write a formula without explicitly knowing what kind of radiation was produced? Okay, so this is still not understood, but something that has to be understood. Like that clearly must be having some deeper understanding, but you don't know what it is. And here this is something that I've already said, that explosion can be regarded as a special case of scattering when the initial state has just one object. Like the same formula you can use, but initially instead of having multiple objects, you just have one, which breaks up into many objects. Now, again, let me emphasize the results that I have given are results in classical theory of gravity. But they are easier to understand as classical limits of some results in quantum theory of gravity. Well, easier is a little subjective, right? What do you mean by easy? If you don't know anything of quantum gravity, maybe it's a classical gravity here. But it's easier only in the sense that it was first discovered in quantum. Right? I mean, this kind of formula was first discovered by taking limits of classical gravity, quantum gravity. And then, of course, we now also have great classical derivatives. Right? So the classical result better have a classical derivative. So now let me explain, give an outline. I will not try to give the full explanation. Give an outline of how it's possible that some quantum gravity results can be used to make classical gravity. Now, the first thing one has to remember in quantum mechanics that quantum mechanics is not deterministic. You don't find what is produced in a given process. Quantum mechanics tells you that if you have a given process, what is the probability of different things being produced. So, with that understanding, let me just introduce some notations. So, in quantum theory of fields, that's the kind of theory that describes general relativity or quantum general relativity. A scattering amplitude is a probability amplitude for transition from one state to another. So, when you talk about a scattering amplitude, A, its absolute value square gives you the transition probability from one state to another. Right? A set of states, a set of incoming state to a set of outgoing. So, let's suppose that we have a scattering amplitude A for transition from one state P to another state Q. So, P contains a set of incoming particles, Q contains a set of outgoing particles. Right? And then mod A square tells you the probability that for that to happen. Now, given A, what the soft graviton theorem gives us is that it gives us a transition amplitude for P going to Q plus some low energy gravitons. Now, what are gravitons? Gravitons are what we call quantum gravitational. You can, when you observe an electromagnetic field, you can either think of this as an electromagnetic field or you can think of as a bunch of photons that are coming to us. Gravitons are just analog of photons or graviton. Okay, so when you talk about gravitational radiation, you can think of it as classical radiation, but you can also equally well view it as a set of gravitons that are possible. So for this discussion, it will be useful to think of this gravitational radiation as a bunch of gravitons that are possible. So what the soft graviton theorem gives us is that if we know the amplitude for P going to Q, some incoming state to some outgoing state, it gives you a way to calculate the amplitude for P going to Q plus some low energy gravitons. It tells us you don't have to calculate it again. Right? P going to Q calculation may be hard, but once you have calculated the P going to Q amplitude, you just have to multiply it by some factors to get the amplitude of P going to Q plus a set of gravitons. So given this, now let's see how we take the classical limit. So classical limit means that we have to first take the external states P and Q to be very massive objects. Right? You cannot think of scattering electrons and treat it classically. Right? You have to think of the external objects to be very heavy. So you take them to be very heavy. And then you calculate the transition probability for P going to Q plus M low energy gravitons. M is some number. Now, this calculation, of course, is very hard because P going to Q calculation will be very hard, typically in a theory of gravity. But what one can show because of the soft graviton theorem is that this amplitude, the M dependence of this amplitude has a simple form, that is A times e to the M over M factorial. A is the constant that measures the P goes to Q transition power. Okay? That's the hard thing to find. B is another constant, but this is the result of soft graviton theorem. P is easy to calculate. Soft graviton theorem tells you how to calculate. And the total probability has this structure, A times B to the M over M factorial. And in the classical limit, one can show that B becomes very large. But B depends only on the initial and final momentum. Okay, that's a consequence of this quantum result in soft graviton theorem. So now let's look at this formula. Right? This is a probabilistic formula. Right? This tells you that you don't know whether one graviton is emitted or two gravitons comes out or thousand gravitons come out. Okay, there is various probabilities. But you can see that if B is very large, then as a function of M, this is a shortly peak function. Okay, in fact, if this function you can easily show that is peaked around M equal to B for large B. Which means that even though quantum mechanics is not deterministic, for large classical objects, for scattering of large classical objects, the probability distribution is very sharp. And it tells us that the probability is almost 1 for only a very narrow range, and then it goes to 0. And that's the classical limit. Right? The classical limit emerges from quantum theory by saying that the probability distribution becomes very sharply peaked. And B is the number that you want, right? This gives you the number of gravitons that are emitted. Right? Even though it's probabilistic, for most practical purpose, you can think of the number of gravitons that are emitted is just D. Yeah, D can be calculated using the soft graviton theorem. And then once you have B, right, we can convert this to a profile of gravitons. You can convert it to H, because number of gravitons can be related to how much the gravitational field is. Right? The more number of gravitons there are, the larger is the gravitational. So this is the way you make connection between soft graviton theorem and this classical results. And the results that I showed you for A, B, F, etc., are all a result of this kind of calculation. You just calculate B using this quantum theory and then turn it into a classical result by assuming that the number of particles that are emitted is very large. Now, this is a quantum derivation, but of course, once you have the quantum derivation, you can also ask how to give a classical derivation. So let me explain how the classical analysis goes. So the classical analysis proceeds like in electromagnetics. How do you calculate electromagnetic wave? You solve Maxwell's equation. Right? You have a source term on the right hand side, and you solve the wave equation with that source. You can try to do the same thing to determine this quantity E mu, right, or which is H mu. You can write other example E mu or H mu. On the right hand side, there is a source term which includes the matter, energy, and momentum. However, this equation is somewhat deceptive, unlike the electromagnetism, where the electromagnetic field appears on the left hand side and the source appears on the right hand side. In gravity, this d mu itself depends on you. Because it's not as simple as it looks. Like I have written it in a somewhat deceptive way, but it's not a simple linear differential that you have to solve. So it's a complicated process because d mu contains E, and the trajectory of the particles, right, which determines the energy momentum tensor, energy and momentum of the particles, they themselves in turn depends on E. Right? So it's really a set of complicated nonlinear partial differential. But let's just proceed without ignoring this complication. Okay? Imagine that we didn't know that d mu depends on it. How will you write the solution? There you use the standard determinant Green's function. So you have a solution. Okay, except that you don't. The reason that you don't have a solution is because right hand side d mu depends on E, right? It's not a solution. It just tells us that this is a relation between E and E. Okay, and you have to then extract E out. Nevertheless, once you have written it this way, now this integral, you see here you have to integrate over the whole of space and time. This is again as an electromagnetism. And this integral now we can divide into what is called a scattering region, where the interactions are taking place in space and time, and then the asymptotic region where only the long range forces are acting on the particles. Because the nuclear interactions etc. happen in a small in some limited region, and outside that the particles are just under each other's gravitational field and electromagnetic influence, right? The long range fields. Now, what I'm going to show is that the behavior of E mu for large, that's what we are after, is insensitive to the contribution from the finite region S. You have this integral over d4y, the finite region. What is happening here doesn't affect how immuno behaves at large Q. Yeah, either at very late time or early time. And the simplest way to understand this is by going to the Fourier space. Instead of using U, right? U is, if you remember, U is a retarded time. You can go to the Fourier space where you're talking in terms of frequency. In the Fourier space, you can show that 1 over U corresponds to a term like log omega in Fourier space, and log U over U square corresponds to a term like omega log omega square in the Fourier space. What is special about these terms is that they are non-analytic. They are not analytic functions at omega equals. Now, what is analytic function? Normally, you think of analytic function as being non-analytic functions as being the ones which become infinite. But that's not the only non-analytic functions we have. This one becomes infinite. Log of 0 is infinite, right? But this is not infinite. Omega times log omega square, if you use appropriate rules, right, you can actually vanish it after omega. But non-analyticity means that if you take sufficient number of derivatives with respect to omega, at some point it will become infinite at omega equals. Okay, that's the meaning of a non-analytic term, and so both of these, 1 over U and log U over U square, corresponds to non-analytic terms in Fourier space. And what one can show is that if you have finite integral, then you can never generate non-analytic terms. Because suppose you have a finite integral, right? It has to diverge somehow. You take derivatives. You can take the derivative inside A. It's still a finite integral. So you can never have it, however many derivatives you take, right? Finite integral will never diverge. So if you are interested in terms like this, the non-analytic terms, we can simply ignore the contribution from this finite. Okay, where that's where all the complications are. And then the asymptotic part, you know that you can ignore all the complicated interactions, right? You know precisely the long range interactions, and that's the way you calculate the results that we mentioned. Okay, so you do the integral only upon that. So this integral d4y that you had, you restrict to these regions where the interactions can be ignored, and you get the results by now solving the equations here. So Ashoke-Graviton theorem was useful in arriving at the result, but these are purely classical results which have purely classical derivatives. So given this, we can ask, does Ashoke-Graviton theorem have any role to play? Right? Did we really need quantum mechanics? Now, the one answer is that no, we didn't, because you can derive it classically. But if you think of it, the kind of question that we answered are not the kind of questions we ask in classical mechanics. So let's remember what kind of questions we ask. We said that we have a scattering process. You have a set of incoming particles, you have a set of outgoing particles, and then gravitational energy. And we said, I give you the incoming particle momentum, outgoing particle momentum. Can you tell me what the gravitational radiation is? This is the question we answered, and Ashoke-Graviton theorem or classical analysis can give you the answer. But if we didn't know about quantum mechanics, in classical mechanics, only the kind of question that normally asked is that you have a given set of initial particles, and you say that, okay, now you tell me what the final particles will be, what the final radiation. You never specify data by saying that you have some initial data and some final data, and then tell you what else is there in the final. So while quantum mechanics was useful in arriving at this result, it's not really necessary to prove this result. But without knowing quantum mechanics, we probably have never asked this kind of question. Okay? A question where you give part of the initial data, part of the final data, and ask what comes. So that, in a sense, is the role of quantum mechanics, okay, which you cannot really apply. So here is for the future. Okay, so we saw that we could get some terms in this expansion for large U. Can we get all the terms? Yeah, there are many non-analytic terms. Like in principle, I mean, if this argument is valid, if all the non-analytic terms could be obtained by this kind of argument, then maybe we can get more terms. That's something to be understood. And then again, we can ask to what extent do such terms depend on the details of the scattering process and not just the initial analysis. Right? That was the whole point of Ashoke-Graviton theorem. And how much we can extend this. So this I'll stop. Thank you.
Okay, let's thank Professor Singh for this extremely profound lecture. Now I think to make real use of his presence, we should take some questions from the audience. So, questions, everybody. Along there. There. Hello.
Thank you, sir, for that amazing lecture. I actually have a couple of questions. I didn't understand some parts of that lecture. So starting with, you mentioned a correction term at the beginning of the lecture, which you related to gravitational drag. Is it has something to do with frame dragging, or what is it? I didn't understand it quite.
Well, it's not frame dragging, it's just that when the gravitational wave passes and it's under the influence of gravity, right? And that slows down the gravitational wave. So normally you think that if you have a distance r, right, you get the time that it takes to travel is r over c. But there is a logarithmic term, right, which comes because of the gravitational wave itself being influenced by gravity. Because gravity influences everything, right? Gravity, light, gravitational wave, light, everything. So it's that correction. So there is a logarithmic term, log r, term proportional to log r. That is the correction.
Sir, thank you for clearing that. My second question is, you mentioned a non-linear memory term. I didn't quite get what it really is.
Okay, yeah, maybe.
And does it have something to do with elasticity of space-time or something?
No, it's not elastic. Well, it may behave like elasticity of space-time, but I'll tell you what it is. Yeah, that we saw this A mu, right? Let me go back one. See, if you look at this A mu, right, what is it? It is telling us that you start from E mu equal to 0. Right? No gravity, E mu equal to 0. By the time the gravitational wave has passed through, E mu doesn't come back to 0, but it comes back to some constant. Which means that if you had started with a interference method whose two arms are the same length, at the end of the gravitational wave passing through, the two arms will not have the same length. Normally, when you think of a wave passing through, the two arms come back to have the same length. So this is what we call the memory term. The nonlinear memory is a particular name for, so let me look at the formula for A mu. You see, in this formula for A mu, you have sum over incoming states, sum over final states. Among this sum over final states, there is also a contribution from the gravitational waves themselves. Those are called nonlinear memories, right? A mu as a whole is the memory term, and the part of the contribution that comes from final state gravitational waves in this sum, that is the nonlinear.
So basically, if we consider this any part of space as like a rubber band, and it gets stretched during when the gravitational wave passes, so it doesn't come back to its original.
Exactly.
And so, can we extract some information from that stretch? Because it still exists, right?
We can, yeah, because there is a formula for A mu, right? So if you can measure this A mu, right, it will tell you this number, this combination. That's the information you extract.
No, after the gravitational wave passes,
yes,
there's still a stretch.
Yes, that is measured by this A mu, right? Because that's the formula. If you look at this A mu appears in the expression for the gravitational wave. So you measure this A mu, and now you can ask what information does it have? The information that it has is this formula, is this combination, right? It tells you a particular relation between the incoming particles and the outgoing particles that actually produce that.
Thank you, sir. And my
excuse me. Since there may be other questions around, I will request you to have these subsequent questions reserved for the tea break in case there are other questions now. Is there any other question? That one, yellow. And then there was a hand raised here. So it's better that one person asks one question at a time, because then Professor Sen can be also approached after during the tea break. so that everybody gets a chance to ask questions.
Thank you, sir, for this wonderful talk. I had a question that why is this theorem called a soft graviton? What's so soft about?
Yeah, so soft means low energy. Right? That is the word we use for soft. Right? So because the theorem involves what kind of low energy gravitational low energy gravitons are being emitted. That's why it's called soft gravitons.
So can we have a high energy counterpart of this?
There is no theorem about that. The high, if you want gravitons with high energy, of course there is some amplitude for producing high energy gravitons, but that doesn't have a simple relation like the soft graviton. Right? For example, this formula that I gave. Yeah, see this formula, that fact that M soft gravitons, the dependence on M is this simple structure, right? This happens only in the gravitational low energy. Right? For high energy gravitons, it is a more complicated formula.
Thank you.
Next question. There was a hand raised there. Yeah.
Thank you, sir, for the nice talk. Regarding this, so,
Please bring the mic close to your mouth.
yeah, so,
No, for everybody.
so my question, I guess, in this slide, you mentioned about a set of particles which is going a transition from P to Q, and after that, the graviton theorem kind of gives us the probability amplitude to in kind of this form, A times B to the power n by B m factorial. So, I mean, the main purpose of graviton theorem is just to give the probability amplitude, right? Because the A factor you've told that it's very difficult to get because
Yeah,
how are we getting from state P to Q?
exactly. Yeah.
So the main purpose is to get the probability amplitude for the graviton theorem.
Yeah. So the main point is that this P is easy to calculate. This is what follows from the soft graviton theorem, right? And the structure. So you see that finally we didn't really need A. We use the fact that this distribution is maximized at some value of A, right? N equal to B. So and soft graviton theorem tells you how to calculate.
So we are discarding A later. So we are not.
Well, you are not discarding with the final formula doesn't depend on it. Right? The final formula for the gravitational flux depends only on B.
Thank you so much.
Okay. Next question. Okay. Okay. Okay.
Thank you, sir, for the talk. Sir, I have some questions, sir. What is this B actually? Means why are we taking it to be large? What does this B physically mean?
Oh, B actually can be calculated in terms of the incoming and outgoing particles. Right? B is related to this factor. I got this formula for A, right?
Yes, sir.
A mu nu. Yeah, so B is roughly this factor.
This is the classically derived.
No, this is okay. This can be derived classically or quantum mechanics. The factor B that appeared in the soft graviton theorem is exactly this factor. Right? And you can see that if P is large, right, this factor becomes large, right?
Yes, sir.
Because there are two parts of P in the numerator and one part in the denominator.
So this is actually the memory term. We can say that B is actually the memory.
Yeah, so B is not just the memory term. So there is this term and then there are corrections which are of which B's. These are also part of B. Okay, so B has an expansion. So B contains information about A, B, C, all of these are inside B.
And so my second question is, sir, if that memory term is there, a space-time fabric is not restored to its original state, right?
Yes.
So, sir, continuous distant gravitational waves are passing through our universes. So, won't it at last tear the space-time fabric?
No, it will not do. I mean, it sees one gravitational wave may give positive shift, another gravitational wave may give negative shifts, right?
Okay,
so
it's not only a positive factor.
Exactly, it's not a positive factor, right? So it keeps going up and down.
Thanks.
Okay, let's move to the next question. There.
Hello. Graviton has no mass, but if the graviton interact Higgs boson field, then the graviton get mass.
No. I mean, the graviton, Higgs boson doesn't give mass to the graviton. Right? Just like it doesn't give mass to the photon, for example. And photon is still massless. So Higgs boson does give mass to many particles, but not to graviton.
Can graviton follow the Schrodinger equation?
Yeah, it follows. It's a quantum particle. Right? So it doesn't follow quite Schrodinger equation, but it follows the appropriate relativistic generalization of the Schrodinger equation.
So please mention the term, say U is very large and U is very small. Then in the slide,
Yes, okay. So that slide you want. Oops, this one, I think I'm going in the wrong direction. This one is, this is the slide?
yes.
Okay.
Please repeat this again for large positive and for large negative, why take this to learn from.
No, this is a final result. Right? And then I said that soft gravitational theorem can be used to derive this result. See, here I have only given the result. Right? It's a result of the calculation that E mu nu for large u, right, which means after the gravitational wave has passed through it long enough, you will find that there is a 1 over u fall off, then there is a u to the 1 over u square log u, and these types of terms. Right? So this is something that comes out of the calculation, and this is the final result of the calculation.
The question, yes.
I think we are all on TT gauge. Yeah.
We are
Working on TT gauge. Gravitational.
TT gauge, okay, that you are time component you are setting use. That's a
other gauge choice is the result will be same.
Yeah, because gauge choice by definition doesn't change physical, right? So result will be the same. Anyway.
There one hand is raised. That corner.
Thank you for this amazing talk. My question is there any experimental verification for
Experimental verification for this? Yeah, not yet. One of the reasons that it is in the standard LIGO experiment that it's hard to verify these results is because the way LIGO operates is that the mirrors are mounted on some retro mirrors. Right? So after the gravitational wave passes through, right, it turns the interferometer back to its normal original position. So that's why LIGO is not suitable for determining either the memory terms or the tail terms. But if you have the space-based experiment, right, these are, for example, the idea is that there will be detectors in space. The interferometer will be in space, and there, of course, nothing is going to put back the interferometer in the original position. So those space-based experiments will be the good ones for detecting effects like this. Right? The effects which switch on at late time or early. So far, neither memory nor the tail terms have been detected.
Okay, we can have two more questions, Parthada.
First is to congratulate you for a wonderful lecture. The question that I have is, you mentioned about electromagnetic memory. Electromagnetic memory.
Electromagnetic memory.
Okay.
Yeah.
You mentioned that there was also a calculation of electromagnetic memory.
Yes.
My question is, what is the observational status? Has this been observed?
No, I don't think it has been observed. Yeah, I think people have tried, but I don't think it has been observed.
No, is that
I think it's hard to set up the so the electromagnetic memory, that the idea is that if an electromagnetic wave passes through and if you have a charged particle on the car, it will start moving, right? And to normally that's not the way you detect electromagnetic, right? You detect electromagnetic wave by the power that it absorbs. So I think to put a charged particle and then follow it has to be lighted, right? Otherwise it will not move very much. So to put a light charged particles and then observing it, right? I think that's quite probably the difficult ways in observe the actual detection of electromagnetic.
If I may be permitted to intercede also further, why isn't it possible to have some charge oscillating which follows its path of the wave and have some current induced in a detector?
I think that will probably die out because these are the ones which are transient but static at the end, right?
it's a permanent effect.
Yeah.
Yes.
See, because this effect is a change in the
Interferometer
effects. It's a change in the gauge field.
I understand.
Right? If you have a change in mu, right? The electric field is not changing.
Yes.
Right. But what has happened is during that process, it has given it a kick.
Yes.
Right, and it moves at that speed. With that speed, constant speed.
Okay, I didn't consume this one slot thing. That was my, yes, yeah, please, Dr. But let's give chance to another student after you.
With a very interesting feature in the overlap of classical and quantum. Of course, we're dealing with this class of states which are called coherent states and so on. The question is, what are the prospects of something like a gravitational laser case?
So that I think is, I mean, very hard. With current technology, I doubt that it will have that kind of. I mean, in a sense, you can say classical gravitational waves are are coherent states, right? But that's not, we will not be satisfied with that, right?
No, because that's very big to see the quantum nature of light for the lasers, right? Lasers have to be quantum.
Yeah.
Other than just coherent light waves.
That's, yeah. I doubt that. Yeah.
But in order to see that, Partha, you would require to form an inverted population inversion of objects that will emit enough gravitational. That itself is a difficult proposition.
Yeah. I think if there is any signature, direct signature of quantum gravity, it will have to come from cosmology. I mean, from all the universe.
Yes.
Or black holes.
Yeah, or black. But black holes also to hard see that. I mean, these kind of quantum effects is very hard, right? Because there is so much classical thing going on near the black hole.
Well, is there the last question? Blue shirt.
I have a question regarding you consider only the momentum in your non-local operators, you considering mu b, and other factors. Yes, but here you talk only momentum, or momentum. Is it asymptotic momentum or the
Asymptotic, yeah. Momentum that comes in from infinity and goes down.
Is there any origin dependent of the wave? If I consider also the binary stars, they produce the gravitational wave. Yes. Is that whole momentum is the origin dependent or the independent? Because the Fourier factor is considered, there is no.
In this context,
Yeah, the point is that's why if you take large U, right, it becomes origin independent. Like for example, take time chord. Right? I haven't said what P naught is exactly. P naught is around the P. But because you are taking the P minus P naught to be large, right, it doesn't matter what the P naught you have chosen. So this formula that I have, the way I have set up the formula, it's not dependent on the precise origin of space.
Okay, since we are having an online component of this discussion, let me read out at least one question that has come from someone called Shreya Karmokar, who basically asked, can you explain about gravitational lensing? I suspect it is in connection with the approach you were suggesting, because she did not elaborate on the question.
But gravitational lensing, okay, I haven't talked about gravitational lensing here, but it's basically that if you have a strong gravitational field, let's say, imagine that you have a very heavy star or a black hole, then just like electromagnetic waves bend, they bend in a medium. Gravitational waves, what will happen is that if you have a very strong gravitational field, they will bend as you go around that strong that object. And sometimes it may happen that they will bend and then they converge. Right? That's the gravitational lens. That you see multiple images because the same object, light from the same object is coming from different directions. Because as it goes around on different sides of the very object, you see images in different directions.
But since that is already explicable in terms of classical gravity, because that is one of the indications of dark matter.
Yeah.
Does she mean gravitational lensing, particularly in your context? I really don't make out what the.
Yeah, but certainly, okay, maybe there is a way to also try to explain gravitational lensing from quantum. Everything after all is quantum gravity, right?
Yeah.
You read the classical limit.
Probably it's redundant to use.
Yeah, it's probably not useful to use quantum gravity to explain gravitational lensing.
Okay. Okay, so maybe we can bring this discussion to a close. First of all, a standing ovation for Professor Sen. Secondly, the undergraduates here wanted to present some memento to him. Let's be witness to that.
ठीक है So that was a wonderful talk. So now the students of presidency would like to present some tokens of appreciation to the speaker and the chair. So if they were. Thank you.
Okay, so now for the organizers to give pose the vote of thanks.
Thank you very much. This was a wonderful afternoon, and so the usual vote of thanks as quickly as possible. So I would sincerely like to express my gratitude first to the presidency administration, particularly to our registrar and to our development officer for initiating many of the things, and great thanks to all my colleagues in the Department of Physics and the School of Astrophysics, and especially to Dr. Mukhopadhyaya, Dr. Ridhuban Chatterjee, and Dr. Shomadip Shamoy. I'm deeply grateful, and they are again big inspirations for me. My thanks to Professor Amitabh Rai Choudhury, Sri Prasad Ranjan Roy, and Professor Parangama Sen for their valuable for coming here and speaking, and Professor Sen's contribution for which I could get the photographs and all this memento that I could present today. Of course, no amount of thanks will be enough for our distinguished speaker, Professor Ashoke Sen, who out of his extremely busy schedule could find time to come to presidency and give this talk. So that's really we're grateful to you, sir. And of course, Professor Biswarup Mukherjee for chairing the session with such finesse, and of course, again, sparing his time with us. And then now I would say that the people without whom it would have been impossible to do the AKR Memorial Lecture, our BSc, MSc, and PhD students. So a big hand, I hope I'm not missing any names. A big hand to Arijit Shah, Anirban Choudhury, Arit Bala, Deepsha Das, Sampurna Bhar, Shagnika Das, Samrat Roy, Moitra Kundu, Shubrajyoti Roy, Shobik Chatterjee, Arif Abdali, Arnotri Samazdar, Soham Chatterjee, and Shagnik Roy. A big hand to all of them. And finally, I have already thanked, and as I said that many thanks to Dr. Sudipta Sengupta for flying. She just came from Delhi to attend this event and to actually meet Professor Sen. That's what she said, that আমি ওনার পায়ের ধুলো নিতে চাই, such a distinguished person, and I'm so glad that you came here. And enormous thanks to the audience who were there all this time and made this program a great success. So now a little bit snacks outside. I would invite you to have some tea and snacks with us. Thank you very much. Thank you.
আমি তো কোথাও এখনো ইউটিউব কোথাও স্ট্রিমিং শেষ করেননি।
না
ওখান থেকে করতে পারবে? বেশ।
স্যার প্রবলেম লাগবে
না,
তো তোমার বোমটা হলো যে তোমার আউটসাইড
আমরা কি আমাদের ছেলেদের জিনিসের গোড়াতে বলতে পারি? কোন অ্যানালিসিস কমপ্লিট আপনারা খুশি? অবশ্যই আমি চেষ্টা করেছি, অবশ্যই অল্প সময়ের মধ্যে আমি কাজটার দায়িত্ব নেওয়ার পরে আগামী দিনে খুব ভালো হয়েছে, সীমিত সময়ের মধ্যে যতটুকু করাইছি। আমি আসছি পরে, আমাকে ফাঁকা হয়ে যাক, আসছি পরে। এইগুলো তো এইগুলো নিয়ে এই অ্যাস্ট্রোল্যাবে রেখে দিয়েছি। অ্যাস্ট্রোল্যাবে দেখবে ওনাদের দুটো বই আছে, তারাও এখানটা ক্লিয়ার হয়ে যায়। আমি তো এখানে কি কি লাইভ দেখাচ্ছি বুঝতে পারছি না, এটা তো জুমটা লাইভ আছে এখনো।
এখনো লাইভ আছে?
আমি তাহলে এন্ড করে দিই, আমি এন্ড করে দিই।